Welcome back, YouTubers, OpenFOAMers, to our video on pimpleFoam. So in this video, we want to talk about so how do we convert a pimpleFoam case, or rather piecefoam case into pimpleFoam case. So of course there are two main things you want to talk about. First thing is, of course, the FV solution dictionary, which we're talking about just now. Of course, we need to, and if you want to maximize our use of pimpleFoam, then we'll want to also modify this control dictionary so that we can use make full use of this capability of pimpleFoam to give us a Courant number solution, i.e. I mean we are able to operate with Courant's number more than 1. So anyway, I'm just going to change the application from icofoam to pimpleFoam in our system control dict in our pimpleFoam directory. And then of course, for reference, we are looking at the incompressible pimpleFoam case in this propeller directory in RAS. So let's clear. So remember, you just go to tutorials, incompressible. So you cd foam tutorials. So cd foam tutorials. Yeah, cd foam tutorials. Then go to incompressible pimpleFoam RAS propeller. So should be pretty easy for you to find if you are familiar with the pimpleFoam directory by now. So first thing first, let's take a look at the system FV solution directory. Okay, so this is the first thing we want to look at. So there is a piezo entry here, which we can just ignore. And I guess you can also give it now a pimple directory. Okay, so I'm going to :W to do that, to save. So what do we need in the pimple directory? Okay, foam. Okay, wrong one. Yeah. This is the standard website I always like to look for in the pimpleFoam. So we need a pimple entry here, all in capital letters. So, oops, this one's the old one from the last video. Let's go to Ubuntu and enter the pimple entry. So not small letters, you need capital letters. Pimple. We write it in. And next thing we need to do is have these non-orthogonal characters and everything in there. So the basic idea behind this non-orthogonal characters is basically to help OpenFOAM, the numerical solvers, with non-orthogonal geometry, meaning to say the mesh will be very unstructured. It won't have a nice grid like this tic-tac-toe looking thing here. So the grids will not be nice square looking grids. Instead, your grids can be very messy. Okay, something like that. It can look very strange and weird. So this is a non-orthogonal grid. This is a non-orthogonal. And I can just delete this away, or delete this away, and delete this away. Alright. Non-orthogonal. This is a non-orthogonal grid. And to help the numerical solver get more accurate results, we usually run through the inner loop maybe 2 more times. So usually we have about 2 to 3 times of this So I'm going to put non-orthogonal characters as 2, and characters I'm going to put as 2, and outer characters, as said before, you want this to be a very high number so that so that we can what do you call that? So that we can have the control, not with the maximum number of iterations, but so this is the maximum number of iterations, of course, but we want the solution to converge before that, and we want OpenFOAM to proceed to the next time step once the convergence reaches, rather than having run out of iterations to do. So we don't want the case where you have maximum iterations reached and then it goes to the next time step, meaning to say it doesn't converge. So we want it to be controlled by the residuals, and of course we want our relaxation factors in there as well. So we can make an entry for pimple. We have non-orthogonal characters, and characters, and outer characters. So this will help to control the pimple algorithm. Alright. This one we can kind of we can enter it or we can leave it out. Doesn't really matter. And we can see the piezo foam. He has n characters equals to 2. So that runs through the inner loop twice. Okay. So n non-orthogonal characters, we want to run it twice as well. Okay, so we can run the inner loop like 2-3 times. So this is like a true pimple thing. So you have many times of the outer loop running, and per outer loop run you have 3 of the n characters. 3 times the pressure loop is running by default, and 2 more times, roughly speaking this is the case, roughly 2 more times is due to the non-orthogonality of our case. And it is so because we use snappy hex mesh to mesh our pipe, and therefore some of the meshes will be non-orthogonal. That should be our expectation. So we want to look at the relaxation factors. So I'm going to copy and paste all of this. Right, copy and pasting all of this. So I'm going to paste it here, insert, and right click to paste. So so copy and paste, I always love it. It works beautifully. So the fields, we want a pressure correction. Instead of 0.3, I'm just going to put maybe 0.4 to help it run faster. And for the equations, we have U, K, and epsilon. And not only that, we might want to put in other fields as well, like omega R and nu tilde. Omega R nu tilde. So we apply this non-orthogonal correction to all of these values. We apply the relaxation factor to all of these values. So we can use 0.4. And of course we can do this as well. I'm going to copy and paste all of this. So copy here and paste here. Oops. Maybe I should switch this here. Switch this here. Okay. Less confusing. Okay. So yeah, this is where this is where the relaxation factors are put in. Okay. So I have a relaxation factor. I've under-relaxed the whole thing. I've under-relaxed the pimpleFoam solver by 0.4, a factor of 0.4. And of course, at the final iteration, we have a relaxation factor of 1. And okay, of course, we want residual control as well. So I'm going to copy and paste this residual control in. This should be inside the pimple loop. So remember, there's a semicolon after all of the entries because this is actually a C++ code, C++ derived code. So please remember, please remember your semicolons. Okay. So the residual controls are basically the U and the P, the velocity and pressure, 1 times 10 to the minus 5, 5 times 10 to the minus 4, and this will be controlling the what do you call that, pimpleFoam algorithm by the once it reaches the tolerance, then the time step iteration stops and it can proceed to the next time step. So I'm going to save and quit WQ. Alright, so we have modified our FV solution. Now let's modify our control dictionary. And let's take a look at the next one. We're going to reference this propeller case, the control dictionary of our propeller case, so that we can see what we can do. I mean, yeah, we can see what we can adjust, what we need to adjust. And if you want to know what each of these settings does, you can take a look at user guide here. This is OpenFOAM version 6. You can look at the version 7 guide, or you can look at the ESI version, openfoam.com. Also, we can take a look at the guides that are written there, though I personally prefer this one. So because I prefer the aesthetics. This is just personal preference. But anyway, let's take a look entry by entry. So we want to start from the latest time as per normal. We want a start time of 0, end time, we stop at end time. So in this case, we want an end time of 1,000 seconds. Okay, end time of 1,000 seconds. And delta t, I will leave it as z, or you can have 1 times 10 to the power minus 5. So you give it a very small time step to start. And instead of right control being the time step, right? So that means, let's say we have 5,000, we have this right interval, which is 5,000. That means every 5,000 of this time step, we save a copy of our velocity and pressure profiles, every single of our piece of data. We don't want to do that, but instead we want this thing called adjustable runtime. And what does adjustable runtime do? Well, let's take a look here. So for one thing, let's take a look. Where is it? Right control, yeah, runtime. Runtime writes data every right interval seconds of simulated time. So if we were to put runtime, okay, so adjustable runtime is an extension of runtime. So I'm going to explain runtime first. Writes data every right interval seconds of simulated time. So that means if I put right interval as runtime here, runtime, what this will tell OpenFOAM to do, or what this will tell pimpleFoam solver to do, is that every 5,000 seconds, instead of 5,000 time steps, 5,000 seconds, then I save a copy, which is not exactly what I want. Okay, so let's say I want to save it every 50 seconds. Now I'll just put 50 over here. Now that's always a very more convenient way of doing things. What is adjustable runtime then? Adjustable runtime is basically runtime, but we can adjust the time step to coincide with the right interval if necessary. And this is used in case of automatic time step adjustment. So what does it mean? So this is, okay, basically there is a way for OpenFOAM to adjust the time step every interval. At every interval, you can adjust the time step automatically. So let's say you want to run at 50 seconds. Every 50 seconds you want to capture, and this is like 49.995. And let's say by default your time step is 0.5 or 0.5 seconds or 0.8 seconds. Yeah, let's say your time step is normally 0.8 seconds. If you were to go by the logic, go by the rationale of adding 0.8 seconds, you will miss the 50 seconds mark. So what adjustable time step will do, or this adjustable runtime will do, it will look at, hey, this thing needs only 0.005 seconds more to meet this 50 seconds mark. To meet this 50 seconds. So instead of having the time step at 0.8 seconds, I'll change the time step to 0.005 seconds so that I can calculate data exactly at 50 seconds of simulated time. So it's very useful for us to say, hey, I want to get my data. We want to get our data at this specific time. So to do that, we use adjustable runtime. So okay, that is using adjustable runtime. So I want data every 50 seconds. Purge write, we leave it at 0, meaning to say we want to keep all our data. Write format ASCII. Write precision 6 significant figures. No write compression. So that's a curious thing. Of course, you can see what write compression does. Oh, this write compression, basically it can compress your files into a gzip when written, on or off. So we generally don't need the write compression. Doesn't take excessively big data. Okay, time format is general, so that's same as here. Runtime modifiable true. What it means is that you can change the control dictionary halfway through your OpenFOAM simulation so that you can adjust your settings. So we wanted to do adjustable time step, right? So here's where the magic happens. These are the two entries you need to enter in. Adjustable time step equals true. Okay, I'm just going to copy this and paste it here. Okay, adjust time step, yes. So semicolon there, max colon number 2. These two entries need to be there to tell OpenFOAM, yes, I want to adjust my time step. So if your time step is too small and the colon number is too small, I want to adjust it such that I have this maximum, I hit the colon number of 2. So that's how pimpleFoam can work. So I'm going to save and quit. And before I start running, I want to do a simple git add. And git commit control dict and every solution for pimpleFoam case added. So git push, I'm going to push it onto my GitHub just before we start running. So it should be pretty straightforward because the changes are very few. Then now we want to change our application from pimpleFoam to pimpleFoam. So I want to change our run files, all our run files. Okay. So instead of pimpleFoam, I'll change it to pimpleFoam. Okay, I'll change it to pimpleFoam. Save and quit. I'll change our run parallel files as well. So instead of removing the pimpleFoam first, let's move pimpleFoam. Restore 0 directory is what we do. This is running, looks like running in parallel. So we run parallel pimpleFoam instead of pimpleFoam. Okay. So everywhere we see pimpleFoam, we just change it to pimpleFoam. See mesh generation. There's nothing much we need to do there because all of this has to do with snappy hex mesh. Okay, so likewise, this one all has to do with Snappy Hex Mesh, nothing to do with pimple or pimpleFoam. So we have an all run parallel, which basically is an all clean first, followed by the mesh generation. Then we have a remove lock pimpleFoam. We change it to pimpleFoam, and we also change the thing here to pimpleFoam. Okay, last one is the all run seri parallel case, and we look at the block mesh, Snappy Hex Mesh. This is the mesh generation, and we want to change the pimpleFoam into pimpleFoam. Okay, so that's all we are doing here. Clear, and let's do all run parallel. I'll put an N here to okay, I can't stop it, so let me git add, git commit run files changed pimpleFoam. This gets a bit messy because this gets a bit messy because I'm running two things at once, so there'll be output being printed, but at the same time I'm trying to do some git pushing, push some changes onto my git. So git push, so now it's running Snappy Hex Mesh. So it's running both of these concurrently, and now it's all okay. Let's take a look at what's going on. So now it's a decompose parallel, so it's running all the decomposed stuff. So remember, there's this cannot remove a lock pimpleFoam. So now, okay, I'm supposed to allow access for pimpleFoam. So Windows Defender loves to have this funny habit of blocking things that you kind of need the most. So let's see lock.pimpleFoam to see whether it's running. So it's at the iteration 3. It's running the solver for XYZ. So the initial residual is so much, but you see the residuals kind of drop very quickly. Okay, so the residuals are dropping. Hopefully it means that, it means that this thing is going to work. Okay, lock.pimpleFoam. So now it's at iteration 5, 6, 7. Okay. So we want, of course, the iterations for U, X, U, Y, and UZ to be below a certain threshold. Okay, so it looks so far so good, and it may take a while for this pimpleFoam to be done. So let's see whether this thing can work. Okay, so funny thing is that now this has appeared to exit for some reason, and okay, let's see what else we need to do to try and make this pimpleFoam work. But at least the pimpleFoam solver is running, and that's good news. We just need to see if we can do this thing in parallel. Okay, I'll see you in the next video. Thanks for watching.